check my first. Okay, 30 bit. Thank you for the introduction. I'm Tanvi Mojwani, and I've been lead data scientist with Amazon Search. And my fun topic here is query understanding within Amazon Search. So I'll try to take you through the use cases where what we do behind the scenes with Amazon. Just by the show of hands, how many people use Amazon Search? Well, this should be a useful topic to you guys. So let's see what's the data science that covers that then, without wasting much time. Okay, this works too. So this is how a typical product search page looks like. You must have seen this several times. You can type in a query at the search bar. We show you relevant products. The decision of showing relevant products is very important within Amazon because this can change your revenue by quite a lot, right? If you don't show the right set of products, then people will buy them less and we'll suffer from revenue loss. So product search is by far the most frequently used tool to obtain products within Amazon, and that determines the revenue of the company. What we do is, given the search query, we hit the query understanding module. So there are two modules to the Amazon search. One is the query understanding part and the other one is the relevance part. The query understanding part extracts features from the user query, and the relevance ranking part then just ranks the product. So on the relevance side, we use gradient boosted decision trees. I'm not going to go through that in this talk, but if you need more details, come catch me after the talk and I'll be happy to share. So this is how a typical product within Amazon looks like. What we have is a lot of structure in our document, unlike the web search. So web search, we rank documents, but they are pretty unstructured text, right? Within Amazon, we have a lot of structure in the products and we want to make use of that. So we know the product description, we know the brand, we know the price of the product, we know it's a Prime product, we know the color, and so on and so forth. We also know how many times you add things to cart, how many times you add it to wish list. So we track all this information and we have massive information on the product side. What we have on the query side is pretty unstructured string of text, right? And what query understanding module basically does, pretty much my team, is how to structure this side of the query so that we can match relevant products. So in this particular long query, we know that it's within fashion categories, so we only surface products within fashion categories. We know that it's a product query. People type all sorts of things on Amazon, like customer service query, like talk to the search engine, that happens too. We categorize things as product queries and surface products only for those. We also understand parts of queries, so we understand that Nike is a brand here so that we can restrict accordingly. We understand the product is shoes, under 200 is the price constraint, someone's looking for a women product, and we are looking for Prime products. So our customers do a good job at describing what they want, and we want to make sure that we value their work and structure that information and then show right set of products. So what are the challenges? I think it's pretty common in search engine to see long tail queries, and we see a large proportion of long tail queries. What we call tail queries are the queries that are basically searched for pretty much once a day. We have no behavioral information, like we don't know how many times people have purchased products for that query. Basically, we have very little data for that query, and we still need to show a right set of products for those queries too, right? So how do we do that is a big challenge. We need speedy search response. So we've seen this in past that we have to give latency within milliseconds to the search engine because customers are pretty restless, right? If you don't see right set of products immediately after you search, you just abandon the site. We've seen that often, so we want to make sure we are quick. We also see dynamic search trends, so our systems should be adaptive to new search queries because products come on Amazon, new products come every day. There's an iPhone 10 release, there is a new book release, there are new movies released, so we want to make sure that our algorithms are adaptive to this. And then we have global reach. So Amazon right now is in 180 countries. We deal with 10 different languages, and with that massive scale and that different languages, our algorithms should be adaptive to these things. So that's a big challenge too. So let's take an example to describe what query understanding does. So in this example, North Face black jacket, we tag North Face as the brand. So we not only know the label is a brand, but we know which particular brand in the catalog it's talking about, so that we can get metadata of that information. We know black is a color, we know jacket is a product. So once we know it's a product and the entity, we can find metadata like what's the category hierarchy. So our catalog is rich with a lot of metadata. Once you just ground a particular part of the query to that catalog entity, you get the metadata for free. So these are all query taggers, and I'll go through the science behind query taggers in quite a bit more details later in this talk. We also do like the entire query analysis. So we take the entire query and say that, okay, let's classify this as a fashion query with a probability of 0.8, which is the score that's shown here. Let's classify this as a product query, and is this a specific query or a broad query? So more the attributes people add in, the more the specific the query is. And these are called query classifiers. So let's deep dive, without wasting much time, on what are the query classifiers. One common query classifier we have is the category query classifier. So within Amazon, if you see that button, all departments, and you click that, you'll see various categories we have within the search engine. Not a lot of users really click the category and search. They just search on all departments. I don't know how many of you all noticed that there is this all departments button, but wow, you are good users. Search more, you provide us training data. But I'll get to that in a bit. But a lot of users, including me, because I know what happens behind the scenes, is we just leave it to all departments and search the query. Now, what the search engine really wants to do is categorize this query into an appropriate category so that we can show products just from that category. So in this case, microwave is mapped to home and kitchen, and we show products from home and kitchen. Now, why do we do this? The primary reason is if we just look at the products from a particular category and our ranker, which is a decision tree, and it's more than 200 decision trees we run at runtime, it needs to be really quick. So if we look at trillions of products within Amazon and rank that, then that's not going to happen. So we only look at the category products, and so that is important for latency. As soon as you save on latency, the abandonment rate decreases. So we've seen that relationship that people abandon the site lesser. There is improved precision, of course. Now in microwave, when we map it to home and kitchen, we only show microwaves. There is hardware cost reduction because now we are only ranking those set of products. Now, how do we do this? A lot of users click category and search on that category, and now we have, these are some examples. Now we have a good training corpus of these queries within the category, right? The major part of my job is actually to get training data, because that's really tricky. Once we get this, so you guys help me doing that, we can use some very standard techniques of text classification. One of the standard techniques is convert these queries into query vectors and then feed it to a softmax layer to do the classification. Now, feeding to a query vector, you can use off-the-shelf pre-trained query vectors that are based on deep learning techniques that we've seen. Or within Amazon, we have this effort of generating our own query vectors using recurrent neural networks, and we basically train that on a language model technique to get the embeddings. So those are various ways, and they're pretty standard for text classification, but the major part is how do you get the training data. I'll quickly go over this, but another classifier I've pretty much told you previously is people not only type product queries, but they also type customer service query, like this customer service phone number, and we want to show right set of widgets. Again, people provide the training data. If you click help button, there is a search engine here, a search bar here, and we see a lot of queries that have been historically typed on this, and that becomes your corpus of customer service class queries. And there is product class queries, which are very easy to find, basically the queries for which there was a purchase in the past. So now you have corpus of class A, class B. You can just do a binary classifier, feed it to a sigmoid layer, and you'll be good. Another one is accessory query classifier. So while I was working with the search engine, I identified this problem pretty long time back, that when people typed queries such as MacBook Pro, you see a lot of accessories. So there are 2 laptops, but a lot others are accessories. What we really want is to just show a clean set of laptops. Now, why that is happening is because our ranker values the number of times a particular product is purchased, right? And accessories are by far purchased way more than base products. So what we did is we had a classifier given a query. Is it a base query or an accessory query? And basically, base product is things like laptop, camera, DSLR, and accessories are all the accessories related to that. So that improved the precision of the system, and the revenue went up by some percentage. Can't disclose that. So So how do we do this? Again, there is a database of base queries and accessory query, and these are the queries that have high purchase rate for this database, right? Now we get the corpus, and we can feed it to a logistic regressor, and we can deploy it to the search engine. So most important thing is, how do we get the training data? Because we have this corpus of base product and accessory product, we could see historically which queries had purchased for those products, and historically a lot of the purchase rate for base queries were a lot more for base products versus accessory query. And so that historic data is golden for us, and we use that for training. Now let's get to the query taggers. I'll talk about the motivation. I think I skimmed through it a little bit before. So if somebody types in Nike shoes under 200 for women, we annotate Nike as brand, and we only show Nike products. We annotate product as shoes, and we only show shoes here. And on the left side, we show what we have done. Everything is clickable, so the user can go with different types of shoes. So our UI treatments are supposed to be interactive, and we show what we've done in bold, so that the users can go back if they don't like it. There's a price constraint here, so if you see everything is under 200, and on left side we've shown what we've done here, that we've understood the price constraint. So it's again a text box, and you can change that. Women's product, and we are talking about prime products, so there's a checkbox here, you can uncheck it. So every time we understand something and we do that, we want to show through a UI, so that if we've done it wrong, to a user can say that I don't want this, I want something else. Another one is improved UI. This is what we call as related brands UI widget. If people type in high value brands like Tissot watches for men, we want to understand that this is a brand and mark that and show results for only that. But we also want to show related brands. This helps in discovering more products and then leading to more purchases. Similarly here, somebody types 2011 C300 Max. We not only understand the year and the make of the car, but we also understand the brand, it's Mercedes-Benz. And we have this filter widget showing what we have understood. So we have an inference engine working behind the scenes after we tag part of the query to understand the brand. So how do we do this? So I'll go into query taggers, specifically how we do brand tagging. So we have this historic set of queries, and suppose we have phrases tagged as brands. So we have like Ray-Ban tagged as brand, Adidas tagged as brand. What we want to do is transform phrase level tagging to word level tagging. So we want to go from here to here. And what this means is, now for each word there is a label associated. This is the begin of the phrase which has brand. This is the inside of the brand phrase, so it goes within the previous phrase. and this is the outside. So this basically mimics what we have here. And similarly for other queries. Now this is a very standard NLP task now. It's called sequence labeling. There are several pause taggers, if you've heard about it, named entity recognition systems. And what we do is we deploy a conditional random field using this as the training data set. I'll skim through what a conditional random field is, but there is a lot of literature on this, specifically the one by Andrew McCallum, and I would recommend you to read that if you're interested. And also go through how do we generate training data, because as I previously mentioned, generating that is the core crux of the system. So what is CRF? CRF is basically a discriminative model versus there is a generative model which is hidden Markov model. What CRF actually does is it models directly the conditional probability. It models probability of y given x. And in this case, I'll explain what this formula is in a bit, but basically your y variables are your begin brand, inside brand, begin color, begin product, the ones that I showed you in the previous slide, and your x variables are the words in the query. So we have, so let's go to what the score means. We have features that are hand-tuned heuristic features that we define, and those are F over here. Right, and we have around M of those features. Now that can be as many features as you want for your particular system. We also have lambda parameters. Now each feature is given a weightage, and what this score does is very simply does a weighted sum of lambda and features over all the words in your sequence. So the first loop is for all the functions, that feature functions, and the second loop is for all the words in the sequence. And this is as simple as taking a softmax on top of it. So we put this in an exponential space and then we normalize it. Now what are the features, right? We can define what we want as features. So a feature could be, you know, if the label is brand for the ith word, then mark it as a 1. So the feature is 1 if we already have the word in the brand dictionary. Another feature, F2, could be if a product, if the label Li is a product and Li minus 1 is a brand, then mark it as 1. Because we've seen very often products follow brand. So a lot of times Nike shoes happen, right? Shoes follows the brand Nike, or Adidas shirts happen. So because of that, we can set these heuristics, which we know through our knowledge that these are the labelings that we've seen often, and those are your features, and it need not be perfect, because then CRF is going to work on having a stochastic gradient descent and decide your lambda parameters. So if a feature is not important, it's going to get lesser weightage. So your lambda parameters are the weights that are decided. Okay, so the how part is how do we get the training data. So we have query logs and then we have product logs. Now think of it as a bipartite graph. We get information that how many times for a query comma product pair people have clicked, purchased, and added to cart. Now we have edge. Edge weight is determined by a function which is a weighted sum of these click add purchases. So we have all this, right? Now take an example of this North Face black jacket. There are edges to all these products. Now we look at the brand of these products. So we go from query to product, and then product to brand, and then we go from query to brand, right? So while going from query to brand, all you do is just take a sum of all these functions. So this is basically taking a sum of this. And so we get 0.8 weight for this query and North Face. Now if you want to convert it to probability space, you can again put a softmax on top of it and convert it to probability space. What we really care about is what's the argmax. So we just take the raw score. We really don't do anything further. And now we want to match this North Face back into the query, because now we want to tag the part of query. How do we do this? We have various matching strategies. One is if the attribute is completely contained in the query. Another one is if the attribute is contained after stop words removal. There is also an edit distance method that I tried out where we look at what is the normalized edit distance and use that. So there's always a trade-off. If your edge weight is a lot, then you can have more partial matches and balance it out that way. So in a gist, we went through query logs, product catalog. I didn't talk about this piece, but this is what business teams gives us. We have some manual overrides, like for this brand, always annotate, for this word, always annotate as a brand. So we have this manual overrides. Based on this, we generate a training data set. We train a condition rapid field, and we deploy this to the search engine. So this is your train time. At the test time, you get a query. You again generate the features. You use the CRF to give you right set of tags, and then use that. Now, what are the pros? We could use a dictionary lookup as simple as that over this, right? But why don't we use that? Sorry, excuse me. One is, this is context aware. So if you see two queries like philosophy books and philosophy face wash, philosophy is a brand in the latter part, right? So this CRF does a good job with that, because in the training data, we never had an edge weight for philosophy books and philosophy brand, right? Versus a dictionary, philosophy will be in the brand dictionary and annotated as brand. We also, if we have more fuzzy matching strategies, we can figure out different ways people call out an entity. So Kate Spade New York is a typical brand, but people just type Kate Spade, right? So we can find all these combinations through this technique. What this technique did is, it increased the precision by 10% over our dictionary-based method and double the recall. So what are the takeaways? One of the takeaways, query understanding is crucial, of course, because my team exists, it is crucial to improve the precision of the system. It is crucial to improve the latency, as we went through, so it's really important. This space is divided into, we can simply divide this into query classifiers and query taggers. There are more parts to it, but that's the overall division that we found out within our team. The innovation for the most problems lies in how do we generate training data set automatically, and we can refresh it every now and then, and that's the main crux of the system. We want to use customer behavioral data, the purchase information, as much as possible, so that we can show right set of products. We are based off Palo Alto, California, so I might sound a bit sleepy. We have some teams in Tokyo, Japan, and Beijing, China. And now I'm open to any questions that you have.
We have about 5 minutes for our questions.
Hi.
Who's talking?
Go for it.
Thank you for the great talk. Question, can you mention maybe some challenges that you have when doing this query tagging for non-English market? So what is changing in your pipeline latent data?
This is a great question. There are a lot of changes, so I very easily describe the English tagger. Things like Chinese are very complicated. Simple things like tokenization. The words are not space-based tokenized, so we have stemming-based tokenizers, and those things are very innate to our search engine. People have built simple text pipeline and tokenizer over years for Chinese language. Those are very different. The other things is our features that I mentioned in some taggers are very marketplace dependent. Because a lot of times people type very differently. Like in India marketplace, people mix two languages too. People use English and Hindi, which is an Indian language, quite interchangeably. And a lot of times people write it in English, but it's a different language. So now you have to be very careful with that. As I say this, we try to be mindful and keep our features very generic, because that just ships our models faster. Once we have got it for a particular marketplace, we can ship it to other marketplace soon. So we try to use behavioral information as much as possible so that it's marketplace agnostic. But sometimes to have good, precision of the system, we have to have some marketplace dependent features. Thank you.
Thank you for the presentation, Tanvi. So I have a couple of questions. So one is about one of the important inputs to your query tagging system is you require the SKU attributes, right? You mentioned about the color and like brand and many other things. Since you have so many new products coming in every day, like do you get all that data automatically, or is it more of like a manual input from the retail team?
Yeah, that's a good question. So I don't handle the catalog team. So Amazon has a huge catalog team which takes care of having clean data from the product side. There's a lot of information that seller gives in. So seller is supposed to tag the color of the query, but a seller can type in any color they want. So we want to canonicalize the colors too. So if a seller says that my product is magenta color, we want to map it to a query which is a red query too. So there's a lot of work happening in canonicalization and synonymity for those words, but that's not what our team handles. We assume that we have all these similar words, and that's why the matching strategy kind of works. I would also like to point there are some deep learning techniques that they have which help in a synonymity situation, because apparently if you have a word vector, it should map to a good location, and that for similar words like magenta and red should be mapping to a similar location, and that helps us. So I think they're working with that, but I have less information to speak for them.
Thank you. I have just one more question.
Sure, go ahead.
So how do you what are your thoughts on how do you tell the difference between like a SKU name versus a category name if those are kind of similar? Like for example, if I were to talk about a grocery SKU, there's something called like spoons or spooners, which is more of a breakfast cereal. And how do you train the data set? It's not like a spoon versus a grocery SKU.
So if I understood this right, are you asking how do we find out different types of categories?
Yeah, if a product name is similar to a category name,
Yeah.
How do you do that?
So in our case, shoes was a particular category that we have. What we have in Amazon actually is a hierarchy. It's not just one layer. What I showed you is all departments and a flat set of categories, but it's not really that simple. There is a root level category, and there are categories below it, and then it follows a whole tree structure. And so for a particular grocery store, we'll have various cereal types and then a subtype of that cereal type. And so we try to map it to as similar browse node or category node that we can. What we have is a multi-label versus a multi-class classifier, because a product can lie in various categories. It could be a cereal, it could be something else that we have within a category in food products. So we have a multi-label classifier in that case. I hope I answered your question.
Okay, one more question.
Yeah, thanks. Actually, I have two small questions. Thanks, Tanvi. Yeah. eBay, we build the same, very similar search capabilities, so this is great. So my question is mostly about your brand recognition part. First is that how do you how do you collect the negative samples when you do training? And the second is, it seems to me like your problem can be narrowed down to just classifying brand versus the same word that are not brand, right? In your philosophy example. So did you talk about, and you think about doing it that way?
Right, so CRF actually, if you just give them the training data of words that have tags of brand with just positive example, it just does a job of training it. It doesn't really need that negative examples. The particular tagger we use is CRF++. It's open source. You can just give it positive examples. There have been some work where we can give, like you mentioned, we can give philosophy books as negative examples, which are still there in the brand dictionary. I think the precision could increase with that. I'm not really aware by how much. But those are some great ideas. We can even synthetically generate negative examples and just have. One last thing is, we did some work on having templates and generating brands and products. So we know for this brand, this is the product. So the training data synthetically generated, and that I know improved our precision. So generating more positive examples helped us.
That's all the time that we have for questions. Let's thank our speaker again.
So